Every human being requires air to extract oxygen. Yet before any of us ever took a breath, we spent 9 months suspended in liquid. There is a common misconception, what some say in English as baby amniotic fluid say oxygen breathe kartahe. That is physically impossible. A developing baby does not extract a single drop of oxygen from the surrounding fluid. In the womb, the fetal lungs are completely filled with liquid. Because of this, they are heavily pressurized and entirely incapable of exchanging gases. With the lungs effectively offline, the developing body faces an immediate engineering problem. It has to acquire oxygen from the outside and route it around those non-working lungs on the inside. The solution to this offline system is the placenta. It acts as the baby's external life support center, temporarily taking on the job of the lungs. Attached to the uterine wall, the placenta pulls in oxygen and nutrients from the mother's own circulatory system to supply the growing fetus. Looking at this cross-section of the exchange membrane, you can see a strict biological boundary. Maternal and fetal blood never actually mix. Instead, particles of oxygen pass across this microscopic barrier from the mother's blood directly into the fetal blood supply. Once that blood is rich with oxygen, it enters the umbilical vein. This single transport highway carries the fresh payload away from the placenta and into the fetal body. Getting the oxygen is only the first step. The body must force this blood past a developing liver and non-working lungs to ensure it reaches the most critical organ of all, the growing brain. The oxygenated blood travels straight up the umbilical cord and immediately encounters its first major hurdle, the fetal liver. To handle this, the anatomy employs its first temporary bypass, a specialized vessel called the Ductus venosus. This 3D vascular map traces the blood flowing up the umbilical vein. Watch what happens at the liver. Instead of filtering through the dense capillary network, the dominant flow shoots straight through this bypass tube, the ductus venosus, and empties directly into the main inferior vena cava. Inside this larger vertical vein, the pure, oxygen-rich blood merges with older, slower-moving, oxygen-poor blood returning from the baby's lower body. This first shortcut preserves both the forward momentum and a high concentration of oxygen, delivering the vital blood right to the entrance of the heart. The blood now enters the right atrium of the heart. In an adult, this chamber pumps blood straight to the lungs. But in a fetus, the anatomy relies on a second temporary bypass, known as the foramen ovale. You can see it in this cross-section. The foramen ovale acts as a one-way biological trapdoor, positioned right between the right and left atria. Blood enters the right side and shoots straight across the center wall into the left side. This happens because the fluid-filled lungs create massive internal pressure. That pressure forms a physical roadblock against the pulmonary pathway, forcing the incoming blood to take the path of least resistance through the trapdoor instead. By skipping the right ventricle and the lungs entirely, the highest quality oxygenated blood is placed perfectly on the left side of the heart, ready to be pumped straight up to the brain. Of course, the flow isn't perfect. A small percentage of blood misses the trapdoor, falls into the right ventricle, and gets pushed toward the lungs. If that blood hits the high-pressure pulmonary roadblock, it could easily back up and damage the developing right side of the heart. To prevent this, the anatomy incorporates a third and final bypass, the ductus arteriosus. This mechanism acts as a precise relief valve. Watching the blood exit the right ventricle, we see it approach the lungs, but it is immediately diverted through a short horizontal connecting vessel directly into the large descending aorta. Once in the aorta, this diverted flow is pushed down to the lower body, eventually splitting off and traveling out through 2 distinct umbilical arteries to return to the placenta for a fresh payload of oxygen. By syncing these 3 shunts, the body maintains a self-sustaining loop that prioritizes oxygen for the brain and heart while the lungs stay completely offline. Fast forward 9 months to the moment of birth. The umbilical cord is clamped, permanently disconnecting the placenta and shutting down the fetal life support system. This is the moment of the Pelly sauce, the very first breath that draws air into the body. The mechanical consequence is instant. As air fills the alveoli, pulmonary resistance drops to near zero, allowing blood to finally rush into the newly functioning lungs. This creates an immediate shift inside the heart. A massive volume of blood returning from the lungs spikes the pressure in the left atrium, overpowering the right side and physically slamming the tissue flap of the foramen ovale shut against the septum. That single breath reverses the entire pressure system of the body, initiating the permanent dismantling of the fetal bypasses. With the internal pressures now completely inverted, the remaining tubular shunts, the ductus arteriosus and ductus venosus, must adapt. The sudden massive influx of oxygenated blood from the working lungs acts as a chemical trigger, causing the smooth muscle lining these shunts to aggressively constrict. Over the next few weeks and months, these closed tubes atrophy. Watching these structures adapt, you can see them completely seal off their internal pathways and harden into fibrous, solid bands known as ligaments. In a matter of seconds, a complex temporary fetal bypass network physically rewires itself, settling into the standard adult circulatory system we all rely on today. This structural transition from a fetal network to a standard circulatory system happens in the seconds after birth. For more insights into the systems that keep us alive, subscribe to BioMatrix Education.